Continuing on physical chemistry, chapter 6, we're beginning section 6 now. We're going to be talking about shifts in ideal gas reaction equilibrium and Le Chatelier's principle. So first, we'll talk about isobaric temperature change at constant pressure. So remember, the derivative with respect to temperature of Kp naught is equal to Kp naught times the change in enthalpy, standard enthalpy, over RT squared. Now we know RT squared is greater than 0, and we know that Kp naught is greater than 0. Therefore, delta H naught determines whether this derivative with respect to temperature is positive or negative. So, case 1, what if it's endothermic? If it's endothermic, that means the enthalpy at standard state is greater than 0. So the derivative of Kp naught with respect to temperature is also going to be greater than 0. What that means is that temperature increases, then Kp naught increases. If temperature decreases, then Kp naught decreases. So that means if you take, if it's endothermic, you're adding heat plus the reactants to get product. So increasing the temperature pushes the reaction forward, or increase the temperature to get more product. Now the other case would be, what if it's exothermic? That means the enthalpy change in standard state is less than 0. So that means the derivative of Kp naught with respect to temperature is less than 0. What that means, if temperature increases, then Kp naught decreases. Or if temperature decreases, then Kp naught increases. So that means we're going from the reactants to product plus heat. So what that means, in this case, we want to lower the temperature to get more product. Now the second process we'll look at is an isothermal pressure change, constant temperature. So let's say we have reactant A going to 2B, and Qp is the reaction quotient. Now Qp is the partial pressure of substance B squared over 2A. Now Kp is equal to the partial pressure of B squared over the partial pressure of A. The difference is K is at equilibrium. Q is at any time. So at equilibrium, they're going to have the same value. Qp will equal to Kp. But when you're not yet at equilibrium, then Qp won't be equal to Kp. Now, let's say that we reduce the volume by 1/2 to make the pressure double. Then we're going to have Qp naught, and that's going to be equal to 2 times the Pb over 2Pa, but this is squared. So we're going to end up with 4 Pb squared, this is partial pressure of B squared, over 2 partial pressure of A. So that means that after causing the pressure to double, our Qp is going to be double what it was before. Now since Qp naught is not equal to Kp, the reaction is not at equilibrium, so the reaction shifts. So Qp prime, I keep saying not, but this 1 means a prime, is greater than Kp. So the equilibrium shifts to the left. That's going to reduce the value of Q prime until Q prime becomes Kp. Increasing the pressure means shifting to the side with fewer molecules. Kp is fixed for a given reaction. It depends on T, but not pressure. Although Kp is a function of temperature only, the equilibrium compositions of reactants and products depend both on temperature and pressure. So here's an example. We have hydrogen plus chlorine giving us hydrogen chloride. That's equation 1. We have methane plus water going carbon monoxide and hydrogen. There's equation 2. There's carbon monoxide plus water giving you carbon dioxide and hydrogen. There's equation 3. Or let's take sodium chloride, add electricity to split them apart into sodium and chlorine. That's equation 4. So here's the apparatus where you have sodium chloride ions, your salt. You run some DC electricity through it, then you end up with the sodium chlorides by the cathode and the chloride ions by the anode. Now pressure has no effect on the equilibrium of composition of equations 1 and 3 because the change in the number of moles of gas was equal to 0. Let me see if I can get that together here so you can see what they were. I don't think it's all going to fit. Oops. All right. You'll have to... Okay, so on the other hand, xi, remember, is the extent of the reaction. We talked about that before. So in the example of N2 gas plus 3H2 gas going to ammonia gas, the change in the number of moles in the gas phase is not equal to 0. Now remember, delta S naught starts at 0 Kelvin. That's something we arbitrarily decided. That's the standard. And it decreases due to delta N being less than 0. So 4 moles goes to 2 moles since delta N is less than 0. So delta G naught is equal to delta H naught at 0 kelvins. So we have delta G, it becomes linear at high temperature just due to the minus TDS term, T delta S term. Now R, natural log of Kp naught, that decreases with temperature due to the change in enthalpy divided by RT squared. Then R times the natural log of Kp naught approaches delta S at high temperature. So we have Kp is equal to Kp temperature. So equilibrium composition changes with P though. So here we go. This is our extent, xi. It goes from 0 to 1. And then temperature. Notice we're going up to about 700 kelvins. So at 1 bar it'll do this, at 10 bars it'll do this, and at 100 bars it'll do this. So shifting the pressure, changing the pressure, overall pressure, is going to change the extent of the reaction. So higher pressure in this example for ammonia is going to give higher xi and more product because we're decreasing the number of moles when we do the reaction forward. So we do the reaction at higher pressure to get more product. In industry, they actually do this at hundreds of atmospheres. Now in this example, the I, what the heck? What the heck? Can't read this. There, oh. Okay, in this example, there is much more product at higher pressure because it goes from 4 moles to 2 moles. But because of this example, the book claims that Le Chatelier's principle is false. It's a long story about whether that's true or not, but make sure you read that section of the book and think about whether you agree with the book or not. Now let's talk about isochoric, remember constant volume, addition of an inert gas, a noble gas. So V is constant, that's what isochoric means. We're going to keep the temperature constant too. The partial pressure of I is the number of moles of substance I times R times T over V, assuming an ideal gas. The partial pressure of I is not affected by adding an inert gas, so the equilibrium won't change. So that means our QP is going to be the product over all substances I of the partial pressure of I to the power of the stoichiometric coefficient of I. So there is no shift in equilibrium. What if we add a reactant gas? So we're going to say that volume is constant and temperature is constant. Then we're going to go from A gas to B gas to C gas to D and to D gas. So we're going to add some A, which means the partial pressure of A is going to increase, which means that QP increases until QP is equal to KP. So we have A gas plus B gas in equilibrium with 2C plus D. So at equilibrium, QP is going to be equal to the partial pressure of C to the second power times the partial pressure of D divided by the partial pressure of A and the partial pressure of B. And that's equal to KP at equilibrium. Then we're going to add some A in this case. Well, the partial pressure of A increases, and then the QP, it decreases. So QP is less than KP. Now let's look at B. What if we hold temperature and pressure constant? We're still adding a reactant gas here. So we have nitrogen gas plus hydrogen gas in equilibrium with ammonia. Now mole fraction, Kx, is equal to 8.33. So if the number of moles of N2, we'll say we start with 3 moles. The number of moles of H2, we'll say we'll start with 1 mole. And the number of moles of NH3, we'll start with 1 mole. Excuse me. X is the mole fraction. So the mole fraction of N2 is 3/5. The mole fraction of H2 is 1/5. The mole fraction of ammonia is 1/5. Now Kx, remember, is the mole fraction of the ammonia to the second power divided by the mole fraction of the hydrogen to the third power times the mole fraction of the nitrogen to the first power. Qx is also the same thing. The mole fraction of ammonia to the second power divided by the mole fraction of the hydrogen to the third power times the mole fraction of the nitrogen to the first power. Just remember that Kx is at equilibrium and Qx means any time. So Qx, this is our starting position. We have 1/5 squared over 1/5 to the cubed, third power, and times 3/5. That gives us 8.33. Now remember, I gave you Kx is equal to 8.33. They're equal to each other, so we're started out at equilibrium. Now, let's add 0.1 moles of N2, so that the change in the number of moles of N2 is equal to 0.1. Then that means N of N2 is now 3.1 moles. Now, Le Chatelier's principle says that since we added reactant, the reaction should go to the right and give us more product. Now here's Qx prime. It's 1 over 5.1 squared over 3.1 over 5.1 over 1.5.1 1 to the third power. So Qx naught is greater than Kx, so the reaction goes left. We actually do get more N2. We added N2, and that caused us to get more N2 back. This is why the book says that this is an exception to Le Chatelier's principle. So that brings up the other question. Is Le Chatelier's principle wrong? Well, here's the deal. If we're adding at constant pressure, then the volume must increase, so the reaction equilibrium shifts in the direction of more moles. This reaction is done industrially at about 700 atm, by the way. So the change in enthalpy is less than 0, so it's exothermic, which means lower temperature is better. This reaction is done industrially about 460 kelvins. So Kx is a function of temperature when delta N gas is equal to 0. But Kx is a function of temperature and pressure when delta N gas is not equal to 0. And remember, we ignore solids and liquids when finding gas. And that is the end of chapter 6.